Welcome to a lesson with Dr. Powell. Let's take a look at this derivative idea um, with a straight line function in 3 dimensions, perhaps given by an equation like this, where this is a vector output and just a number input parameter. And suppose we have something like this and that. Now, normally, if we want to take a derivative, we've done this before. We just do it component-wise. Now, how do we think about that, though, in terms of this projection idea? Well, if we just take a little section where in the t variable, you have a run of +1. So +1 is equal to the change of t right here. Then what are we going to get? Now, the rise and how much the output changes from place to place is actually a vector itself, because we have 3 different components. And you think from here to here, I mean, literally, we're seeing what the change, this vector right here is literally the change of r, how much r is changed. I mean, r itself, you could think of, if you think of these points as being vectors, I mean, they're vectors away from the origin. And if t is changed forward like this, then the vector right in between is actually the change of r. And so what we'd like to do is to figure out the rise. The rise is represented by this vector, but usually we can think of the rise in terms of 3 rises, the rise in each component. So what we could do is we could take this rise vector right here and project it onto the x direction. And suppose this is x direction, and the projection should be should be 2 if the run is 1. That's because this is like change of, this is like a because what we're considering is we're considering what the change of x is. So we want to know what the change of x is if the run is changed by 1. So if change of t is just 1. So if change of t is 1, then this is equal to change of x, and this is also equal to the slope in the x direction for a change of t. So that would be 2. So we know if we have a run of 1, then in this direction, the x direction, we have a rise of 2. In the y direction, we have a rise of 3. And in the z direction, we have a drop actually of -1. And so in this sense, this the derivative that we've been talking about has a lot to do with projections, just in different directions, because we can think of there being 3 different rises. So 3 different rises for one single input value. Now, as we go along notationally, we're actually going to represent this as follows. For every single input for our functions, because our functions are going to have different numbers of inputs now, we're actually going to have vectors coming as inputs instead of just outputs. So we're kind of going to beef that up a little bit. But for every single input value, we're going to have a column. So we're only going to have one column here because we only have one input value. And then what we're going to do is we're going to represent these guys, these rises per run of 1 here of this particular input value. We're going to represent the different rises that we have just in a column format like this: 2, 3, -1. That's going to be notation as we go on and look at different functions for the actual derivative, which we'll call the total derivative of this particular function. And we'll notate it this way. So, and we're going to be thinking of this as being a matrix, and we'll get more into that in later videos. Thanks for watching.